Ever imagine building a circuit using a glass jar full of water?
Really?
Yeah. Believe it or not, that's what the first capacitors were.
Oh, wow.
They were called Leyden jars.
Huh.
It's amazing to think something so simple kind of paved the way for the sophisticated capacitors that we have today.
Yeah, it really highlights how those fundamental principles can drive technological advancements for centuries.
Right.
And even though we've come a long way from Leyden jars, the basic idea behind a capacitor is still the same: storing electrical energy.
Absolutely. And for our viewers who are passionate about electronics, we're going to take a closer look at capacitors, how they work their diverse applications, and why understanding them is crucial for anyone who's working with circuits.
We can skip the basic definitions. I think your audience is already familiar with all that.
Right, they are.
And we can just jump into the fascinating nuances.
Perfect. So let's talk about how a capacitor actually stores energy.
It doesn't store energy chemically like a battery does.
Yeah.
Instead, it utilizes an electric field.
Okay.
So imagine two conductive plates, and they're separated by an insulating material. We call that a dielectric.
Okay.
And when you apply a voltage across those plates, you create an electric field in the dielectric.
So the electric field is the key here.
Yeah.
But how does that actually store the energy?
Think of it like stretching a rubber band. You're putting energy into stretching it, and then that energy is stored as potential energy.
Right.
Similarly, creating that electric field in a capacitor, it requires energy, and that energy is stored within the field itself.
Okay, that's a helpful analogy. But what's happening on the plates themselves?
Well, as the electric field builds up, positive charges accumulate on one plate and negative charges on the other. And it's this separation of charge that represents the stored energy. The greater that charge separation is, the stronger the electric field and the more energy the capacitor can store.
So it's all about building up that electric field and separating charges.
Yes.
It's fascinating how something that sounds so abstract can be so crucial in electronics.
And it's important to remember that the type of dielectric material, it plays a critical role in how much energy a capacitor can store. Different materials have different permittivities.
Right.
Which is a measure of how easily they allow an electric field to form.
So if you want to pack more energy into a capacitor, you need a dielectric material with a higher permittivity.
Exactly. That's why you'll see a wide variety of dielectric materials used in capacitors.
Yeah.
From ceramic, the plastic film, to tantalum.
Wow.
Each with its own advantages and trade-offs.
This brings up an interesting point. If we're aiming for higher energy storage, why not just use the material with the highest permittivity available?
Well, because in engineering, it's all about balancing all these different factors. While a higher permittivity might sound really appealing, it often comes with compromises. For instance, some high permittivity materials, they might have higher leakage currents, meaning they lose charge over time, or they might not perform well at really high frequencies.
So it's not just about maximizing one parameter.
Exactly. Selecting the right capacitor involves considering the entire application. The capacitance, the voltage rating, the operating frequency, and even the physical size constraints. You have to think about all that.
Sounds like a real balancing act.
And this is where understanding all the nuances of capacitors becomes essential for making informed design decisions.
So we've talked about the dielectric materials and their permittivity, but how does that actually translate to the capacitance that we see in the data sheets?
Well, that's where things get a little bit more technical. The capacitance of a capacitor is measured in farads, and it's determined by a few key factors: the permittivity of the dielectric material, the surface area of the plates, and the distance between them.
So if I'm understanding correctly, a larger surface area or a smaller distance between the plates would result in a higher capacitance.
Exactly. It's all about maximizing that electric field strength within the dielectric.
Okay.
And that's why you see such a variety in capacitor designs. For example, some capacitors, they use multiple layers of plates and dielectric to increase that effective surface area, but in a small package.
That makes sense. It's like squeezing more storage into a smaller space.
Right.
But I'm curious if we can increase capacitance by simply, reducing the distance between the plates. Why not make them incredibly close together?
Well, there's a limit to how close you can bring those plates together. If the dielectric is too thin, the voltage across the capacitor could cause it to break down and lead to a short circuit.
So there's a trade-off between maximizing the capacitance and making sure that the dielectric can withstand the voltage.
Exactly. And this is where the concept of dielectric strength comes in. It's a measure of how much voltage a dielectric material can actually withstand before it breaks down.
I imagine this becomes even more critical when we're dealing with high-voltage applications.
Absolutely. In those scenarios, you need a dielectric material with a really high dielectric strength to prevent those catastrophic failures.
So it's a constant balancing act, optimizing capacitance, voltage rating, dielectric strength, and of course, cost and size considerations.
It's a very complex puzzle, and it's this complexity that makes designing circuits with capacitors both challenging and fascinating.
All right, speaking of challenges, one thing I've always found kind of interesting is that real-world capacitors aren't perfect.
Yeah.
They have their own limitations, right?
You're absolutely right. In a perfect world, a capacitor would charge and discharge instantly.
Right.
And it wouldn't lose any energy, but in reality, there are some inherent losses and non-idealities.
Unlike what?
Well, one major factor is something we call equivalent series resistance, or ESR. It's essentially the internal resistance of a capacitor, and it can limit how quickly it can charge and discharge.
So a higher ESR would slow down those processes.
Exactly. And that can be a real problem in applications where you need those rapid charge and discharge cycles.
Right.
Like in high-speed digital circuits or switching power supplies.
It sounds like ESR is something engineers need to pay close attention to.
Definitely, it's a key parameter to consider, especially when efficiency and speed are critical.
And are there other non-idealities that we should be aware of?
Yes. Another important one is something called leakage current. It's a small amount of current that actually flows through the dielectric, even when the capacitor is supposed to be blocking the current.
So it's like a tiny leak in our energy storage tank.
That's a good analogy.
Right.
And while that leakage current is typically very small, it can become significant over time.
Yeah.
Especially in applications like long-term energy storage or high-precision timing circuits.
It seems like understanding these non-idealities is just as important as grasping the fundamental concepts.
I agree. It's this deeper level of understanding that really separates the novice from the expert when it comes to designing and troubleshooting those circuits with capacitors.
Okay, so we've covered a lot of ground, from dielectric materials to capacitance calculations to the real-world limitations of capacitors.
And with that solid foundation, I think now would be a good time to jump into some of the fascinating applications of capacitors.
Perfect, because it's one thing to understand the theory, but seeing capacitors in action, it really brings it all together.
Exactly. So let's start with one of the most common applications.
Okay.
Filtering.
Filtering, how do capacitors help us clean up electrical signals?
Well, remember how we talked about capacitors? They block that DC current while allowing the AC current to pass through?
Yeah, that was because the constant voltage of DC couldn't create that changing electric field in the capacitor.
You got it. And this property makes capacitors absolutely perfect for separating AC and DC components of a signal. For example, let's say you have a power supply that produces a bit of AC ripple on top of its DC output.
It's a common problem, especially with switching power supplies.
Right. To smooth out that ripple, you can use a capacitor as a filter. The capacitor will act like a low-pass filter, blocking that high-frequency AC ripple, but allowing that DC component to pass through.
So it's like a sieve that separates the unwanted noise from the desired signal.
A great analogy, and this filtering capability of capacitors is used in countless applications, from audio circuits to power supplies to communication systems.
It's incredible how such a simple component can play such a crucial role in shaping the quality of electrical signals.
It really is, and filtering is just one example. Capacitors are also used for energy storage timing circuits, coupling signals, and even creating resonance circuits.
Speaking of energy storage, I remember reading about supercapacitors,
Yeah.
which can store significantly more energy than traditional capacitors.
Supercapacitors are fascinating. They're essentially bridging that gap between traditional capacitors and batteries.
How do they achieve such a high energy storage capacity?
They use a combination of high surface area materials
Okay.
and extremely thin dielectrics.
Uh-huh.
This allows them to store much more charge than a conventional capacitor of the same size.
And I imagine that opens up a whole new world of possibilities for applications where we need high energy storage but can't rely on batteries.
Absolutely. Supercapacitors are already finding their way into applications like electric vehicles, backup power systems, and even energy harvesting devices.
It's amazing to see how that humble capacitor, with its, simple principle of storing energy in an electric field, has evolved into such a diverse and powerful component. One area where I think capacitors have had a really profound impact is in computing.
Oh, absolutely. Capacitors were essential in developing the early computers. They served as a form of dynamic memory.
I can imagine that must have been quite a challenge back then, using capacitors to store data.
It certainly was. Those early memory systems were massive. They used banks of capacitors that required constant refreshing just to maintain the data integrity.
Refreshing. Why was that necessary?
Well, remember how we talked about leakage current? Even just a small amount of leakage can cause the charge that's stored in a capacitor to slowly dissipate.
So refreshing was essentially a way to compensate for those losses and keep the data intact.
Exactly. It was a constant battle against leakage, but it did pave the way for more sophisticated memory technologies that we have today.
Well, this has been a really enlightening journey through the world of capacitors.
It has been.
Thank you for sharing your insights and your expertise.
It was my pleasure.
And to our viewers, we are AI experts.
That's right.
If you enjoyed this exploration of capacitors, be sure to like and subscribe to our channel.
And don't forget to leave your thoughts and questions in the comments below.
Until next time, keep exploring that fascinating world of electronics.